Greetings, math friends. In this video, I want to go through an exploration. One of the things that you may have wondered is, how do the theorems get discovered? How do they end up in a textbook? So we're going to start out with a circle with center C, and we're going to ask the question, how does a central angle relate to an inscribed angle? And then as we explore that, we can formulate our conjecture, our idea about how we think they relate, and working through the geometry of this, we can then say whether this is a true statement or if it is a false statement. And that's really part of how mathematical discovery works. We observe something, we try something, we guess what's going on, and then we have to prove if that guess was accurate or not. So first of all, we need to draw some angles in here. The first part is the central angle. The central angle is an angle that starts at the center of the circle and its rays pass out to the circumference. So this was point C. It was the center of the circle. I'm going to assign some points here. So let's just call these A and B. And then the next thing that we need to have is an inscribed angle. And instead of putting the vertex of the inscribed angle directly above C, where we might fit them on a straight line passing directly vertically through the circle, I'm going to put it off to the side because I want something that I'm not going to be tempted to assume something about this interaction that may not actually be present. So I don't want anything to look too lined up. So over here, I'm going to choose another point here, and maybe I call this E. And then I'm going to connect that point to the two previous intersections. All right, so now I have, this is my central angle and this is my inscribed angle. So I have this quadrilateral here. This is a concave quadrilateral that's inside my circle, and I want to know the measure of this versus the measure of this. So we have angle ACB, and we have angle AEB. All right, and we want to know what the relationship is here. Is this angle equal to this angle? Is this angle greater than this angle? Or is this angle smaller than this angle? So options we have: equal, less than, greater than. So this is option 1, option 2, and option 3. So in the conjecture phase, you would say one of these things that you believe it is, and then you would try to prove that situation. Let's just say that we believe this angle is greater than this angle. So let's say that we want to prove number 3 here. We're going to go through and make an argument here and see if we can establish the relationship between these, and then we can either reject this or fail to reject this. So is this true or not? To start to begin the argument that I want to make it would be helpful to have triangles in here. We learn a lot about triangles in high school mathematics. So I'm going to add an auxiliary segment between A and B, and that's allowable because between any 2 points there is a line. That's one of our postulates in geometry. I can further connect point E through C for the same reason and create this triangle. So I have a triangle between B, this intersection, and E. That's a big triangle. I have the triangle BCE, that's another triangle, and then I have the triangle CB, and then this intersection. I'm going to go ahead and name this intersection. We're going to call that intersection G. And then what I'd like to do is I'd like to pull this over to the side and just focus on these triangles. Now that we've pulled this triangle off to the side, we can look at the properties we have here, and then when we reinsert this into the circle here with these angles, it will tell us something about the diagram that we had with the central angle and the inscribed angle. One thing that we can notice is that between C and E and C and B, this is the center of the circle, and these 2 points are on the circumference, so that means that this and this are radii. So CE is congruent to CB. That means that we know that this angle here and this angle here are going to be congruent by the isosceles triangle theorem. So angle CEB is congruent to CBE due to the isosceles triangle theorem. Since ECB and GCB are adjacent angles on a straight line, we know that this is a linear pair, which is also a supplementary pair. So this angle plus this angle is 180 degrees. So GCB plus angle BCE is 180 degrees. This triangle, which we've identified as isosceles because we have these 2 congruent sides, these 3 angles interior here are also equal to 180 degrees. That is the triangle angle sum theorem. So extending this a little bit, CEB plus CBE plus ECB, BCE is also 180 degrees. And then we can observe that this angle and this angle match. So that tells me that this angle here and these 2 angles have to have the same measure, since the sum of this is 180 degrees and the sum of this is 180 degrees. By transitivity, this and this have to be equal, and since these are equal, they are the same, they're congruent, they're exactly the same, they're the same angle, then that means that these 2 add up to this. So CEB plus angle CBE is equal to angle GCB. So GCB right here is the same measure as these 2 angles. Well, these 2 angles were congruent, which means that I can replace this statement with 2 times choose either one of these. In this case, I want CEB because this was the angle we were interested in. CEB equals angle GCB. And GCB was the angle that we were interested here. This tells me that this angle here has to be smaller because it takes two of these to make one of these. That's what we have here. Two of these is equal to one of these. So to answer our question here, we have said two of this portion here is equal to one of this portion here. So that's indicating to us that our conjecture is going to be correct if it takes a couple of these to make one of these. However, this is not a proof yet of this diagram because we've only looked at a portion of the angles that we have over here. If I had this point over here where when I pass the line from EC through and it met at 90 degrees here, we could have just multiplied each of these angles by 2 to get the larger angles, and we would have been done. This is why I specifically chose E to be off a little bit, so that when I did pass this line through, I would not have a perpendicular here, because that might lead us to a false conclusion that we had really shown everything we needed to show, when that would have been one special case because it was a specific angle that was made in this intersection. And we don't want that. We want this to be done in general, and we don't know specifically what these angles are at this point. We really need to look at the left-hand side of this diagram, and we can pull these triangles out over here and do the same argument over here, and that's what we want to do. It's very symmetric to the argument that we've done here. Now that we have these details written out, we want to observe that just like we had over here, this angle and this angle are included. These are the same angle. Since the sum of these angles equals 180 degrees and the sum of these angles equals 180 degrees, that means these two statements can set, the two left-hand sides of these can be set equal to each other by transitivity. So subtracting these out, this angle here has to be equal to the sum of these angles here. So angle ACG is equal to angle EAC plus angle AEC. Then we also want to observe that these two angles here are congruent because they are the angles in the isosceles triangle, so we can rewrite this. Angle ACG is equal to 2 times angle AEC. What we've concluded is that it takes two of these angles to equal one of these angles, which is the same conclusion that we drew over here. So we see in the original diagram that two of these equal one of these, and we previously concluded two of these equal one of these, still giving us that this big angle, the sum of that, is going to have to be bigger than the sum of these two angles, which is leading us toward this conclusion that this is in fact true. So to finish the proof, we have to show that the entire sum here is greater than the entire sum here. So we're just going to take these two statements and add them together. ACG and GCB added together make ACB. So this angle plus this angle. So we're going to add those together and add these two together. Angle ACG plus angle GCB has to be equal to 2 times angle AEC plus 2 times angle CEB. And then we can clean this up a little bit. These two we've stated is ACB, so this is angle ACB. And then we can factor the 2 out. So this is angle AEC plus angle CEB. And we know that these are these two angles here, AEC and then CEB. So that's this. So we can replace this here. And with that statement, this is the statement that we need to conclude the proof that this is larger than this angle. We see here that it takes 2 of these to equal 1 of these. So we have now proven this as true, no question. We have a greater conclusion that we can draw from this, though, that we've learned in this journey, and that is what we call a corollary. When we prove one theorem, this becomes our theorem because we've proven it. And when we discover something from that theorem that is a statement we can also make that is even stronger, in this case, than the original theorem, then we call that a corollary. So what have we learned that's a stronger statement than angle ACB is greater than angle AEB? Well, we've learned that angle ACB is equal to 2 times angle AEB. So this, we just know one is larger than the other, and we don't know how large they are. In this particular case, we know exactly how large they are, that this is twice as big as this. So over here, I have stated a corollary. A central angle is twice the measure of the inscribed angle. And then I have one more idea here that is included in the diagram that's important. We have to know that the central angle and the inscribed angle are intercepting the same arc, which is this arc AB here. So that is important because these essentially overlap. We don't want the inscribed angle to be like going this way and the central angle going this way. That's not what we proved here. So we have to make sure that when we state our corollary, the thing that we learned from the theorem that we proved, that it has all the details that we learned from the theorem that we proved. Now, once you state a corollary, you do have to prove this also, because this is essentially a baby theorem. It's something that we learned from proving the theorem that we did. In this case, typically in any case where you have a corollary that you're going to prove, we've essentially already provided the details in the theorem. We just need to pull out the details that are relevant to the corollary and use that as the proof for the corollary. So you don't necessarily have to come up with a lot of incredibly new work. You just rework the things that you have here. Some of you in the proving of this particular theorem might say, well, this is a lot of work and it could have been done more efficiently. That is probably true. We have to remember, though, that we started this out as an exploration. And in mathematics, that is something that we are allowed to do, is we are allowed to explore. And as long as we don't violate the postulates and the axioms that are the underlying rules for the system that we're working in, there's a lot of freedom to do that. Many times you see in like a language class or a history class that you have a rough draft when you write something and then a final draft. And you may not have heard that as much in a mathematics class, but it is still very relevant in a mathematics class. You can work out some things, it can be messy, and then you can go back and write out a final draft of that work. In particular, with things like this, where we've explored some things, we had a theorem that we wanted to try to have a proof for, you can go back now that you have all the details, and you can clean up and make this more efficient if you want to, and that's perfectly fine. Also note that for a theorem, my proof may not match your proof. As long as they both use the right logic and they don't violate the axioms and postulates, and you come to the same conclusion, then it's a valid proof. So our proofs don't have to match each other to actually do the job that they need to do. And that's an important thing that we need to realize as well. So hopefully you find some mathematics in your part of the world to be able to share with others and to enjoy. Cheerful calculations.